Okay, everybody, I think we're going to look at something kind of fun here. Um, a question that I'm sure has been floating around your mind for a long time is, how long is it actually on one of these sine waves? And we're going to look at the calculus that helps us calculate a length of this sine wave, not just a sine wave, but any curve. What's the process? How does it work? So what we're talking about here is distance, and if we had a line, then we know how to find distance. Okay, we have a distance formula that we use to find the linear distance between 2 points. Okay, and that's the square root of the change in x squared plus the change in y squared. Okay, we've done that for a long time. The cool thing here is that we know that on smooth curves, when we zoom in, they look like line segments. Okay, they're very, very close to line segments. We're going to exploit this fact here to help us set up a process to find the exact length of a curve. Okay, so if we go back to the sine curve real quick, what we would aim to do here is chop this interval into pieces that are small enough to the point where this curve looks like a line segment, okay, for a while, and calculate how far is it from one endpoint of the interval to the next endpoint, and then do that for the next interval, and the next interval, and the next interval, and add up those distances, and that would be a pretty good approximation, okay? And let's actually go ahead and take a look at that. Let's say that we went from 0 to pi, because I could double that answer, and that would be a pretty good approximation because I have a curve that's symmetric about the x-axis. And if we use 12 subintervals, then each subinterval is pi over 12 units long, which is roughly, if pi is roughly 3 and 3/12 is roughly a quarter of a unit. Okay, if we go back and look at this picture real quick, a quarter of the unit when you zoom in is almost looks like enough to make this curve look like a line. Okay, so if you did that, you would have 12 different distances to add up. Okay, and I just kind of want to show you what some of these distances look like. I'm actually going to calculate these each individually and show you, but in the first subinterval, okay, the change in x is always going to be pi over 12. So that's not going to change in any of these calculations, but there's pi over 12 squared. And then the change in y is the sine of the right endpoint minus the sine of the left endpoint squared. Okay? In this case, it comes out to be 0.368. In the next interval, which is pi over 12 to pi over 6, the calculation is very similar. Okay, the change in x is still pi over 12 squared, and now you have the sine of pi over 6 minus the sine of pi over 12 quantity squared. It comes out to be 0.355, etc., etc., etc. Okay, we'll look at one more, and then hopefully we'll see the pattern here. In the third interval, pi over 6 to pi over 4, we still have pi over 12 squared plus the sine of the right endpoint, sine of pi fourths, minus the sine of the left endpoint, pi over 6, quantity squared. We get 0.338, etc. Now, in each of these calculations, there's some similarities. They all have the pi over 12 squared. They all have a addition to another quantity squared. And then each of these is a difference of two sine values. And these sine values differ by one of the delta x's. Okay, 0 to pi over 12 to 2 pi over 12, 2 pi over 12 to 3 pi over 12, etc. And these pi over 12s increase by 1 unit each, or 1 delta x each time. Okay, and so this is a situation that is set up perfectly for a sigma exploitation. Okay, so here's what the sigma would look like in this case. Okay, I would say I'm going to double my answer, but I'm going to go from k1 to 12, so 12 subintervals that look like delta x, which is pi over 12, squared, plus the sine of my counter times delta x. So remember, my counter starts at 1, ends at 12, minus the sine of my counter minus 1 times delta x squared. So for loop 1, that would be sine of 1 delta x minus sine of 0. That's what you have up here. Delta x is pi over 12 in this case. Lap 2 would be sine of 2 pi 12, so that's pi 6, minus the sine of pi 12s. Okay? And then the final loop would be the sine of 12 pi 12s, or pi, minus the sine of 11 pi 12ths, which would be the last subinterval. Okay? So sigma does this calculation for you very nicely and quickly and gives us 7.6335 as an approximation for the length of the sine curve from 0 to 2 pi. Okay? Now, we have seen where sigmas have become integrals when you make your subintervals very, very small. And that's what's going to happen here also. But I want to take you through that calculation just so it doesn't seem like it's magic when it pops up for the first time. Okay, so here's the deal. We have an expression that tells us here's the length of n line segments, okay, when you've chopped up your curve into pieces. Delta x squared plus f of your starting value plus k times the delta x minus f of starting value plus 1 less delta x squared. Okay, this expression in here is pretty bulky. Okay, so we're going to replace it with this convenient little symbol here. Okay, delta y, because these are changes in y's, sub k. Okay, this is telling you what is the change in y in the kth subinterval. Okay, in our example there were 12, but in general, if you chop an interval into n pieces, there are n subintervals, and this is how you would calculate the delta y in each subinterval. Okay, so this now would become a little bit more manageable to write. We have sigma of delta x squared, and remember that delta x is defined as a constant, whatever we determine our interval to be and how many pieces we want, plus delta y quantity squared, or delta y sub k quantity squared, I should say. Okay, we're still going from k equals 1 to n, and now we want to do some interesting algebra here to help us out and come up with some interesting symbols that we've seen before. All right, inside the square root sign, we're going to multiply by 1 in an interesting way. Okay, so today we're going to multiply delta y sub k squared by delta x over delta x quantity squared, and I'm actually going to multiply that by the entire inside of the square root. So let's see if I can bump this over. I can't. Okay, let me rewrite this real quick. I'll pause the video and come back. Okay, so this is what I intend to do. I multiplied the inside by 1 in the form delta x squared, or delta x over delta x squared. And now we're going to move some things around here. Okay, I'm going to take one of those delta x squareds outside of the square root. Okay, and when it comes out of the square root, it becomes just a delta x. Delta x is a positive, so I don't have to worry about absolute value here. Okay, so I took one of those delta x squareds out. There's still 1 over delta x squared on the inside. And I'm going to distribute that to each of the pieces on the inside here. So this would now be, excuse me, this would now be delta x squared over delta x squared, which is kind of a nice expression to have here. And the second piece will be plus delta y sub k squared over delta x squared. Okay, so again, where did that come from? I split up this fraction right here. I took one of the delta x squareds outside. That left a 1 over delta x squared on the inside, which I then distributed to each of these two pieces. I still have my sigma notation. I'm still going from k equals 1 to n. And now we're going to, again, rearrange a few things in here. This is now 1, and I'm just going to write this as a fraction being squared. There's still a delta x here on the outside. Okay, what is the fraction that's being squared? Well, it's delta y sub k over delta x. Okay, which is basically the slope of the secant line between 2 points, the two endpoints in that subinterval. Okay, and we're about to do one last thing here to make this magical. Okay, k equals 1 to n. Okay, and so the idea here is we want to take as many pieces of the curve as we can, chop them very, very thinly until we have the exact answer. And so to do that, we need to take the limit as n approaches infinity. Okay, so let me write out the expression here. The limit as n approaches infinity of what? Well, the sum of all these pieces starting at 1, stopping at n, of the distance of the line segments that they create, which is 1 plus delta y sub k over delta x, that quantity squared, times delta x. Okay, now there's a couple of things to note here, okay? As n approaches infinity, delta x gets tiny, okay? Change in x gets very close to 0, and delta y over delta x approaches y primed, or dy dx, okay, however you want to write it today. Okay, in other words, the slope of the secant line, when you make those 2 points very close together, becomes the slope of the tangent line. And we've seen how a Riemann sum, when you take its limit at infinity, becomes an integral. And so this is now the formula for the length of a curve. It's the integral from a to b, because remember a and b are built into the delta x, of the square root of 1 plus, this is now the derivative of your curve, dy dx, squared, and then that delta x there becomes the dx in the integral, okay, by definition. When we first saw an integral, this is what it meant. We've now used it in a new context. So this is how you find the length of a curve. It's kind of a funky formula. It takes some memorizing, but it's derived from what we just did to approximate, so hopefully it makes a little bit of sense to you. Now, initially here, there's going to be very few integrals you can actually do by hand this way. A lot of these will end up being calculator problems, but the ones that they do give you are kind of neat and fun, lots of algebra involved, and we're going to show you a few new techniques to help you do some of these. Okay, so first of all, let's go ahead and go back to the one we just were trying to answer, which was how long is the sine curve, right? How long is the sine curve on the interval 0 to 2 pi? And this is a calculator one that we'll tackle first. So let's set up the integral first. So the length of the curve will be the integral from 0 to 2 pi of the square root of 1 plus, what's the derivative of sine x? Well, it's cosine x, and you have to square it. So 1 plus cosine squared x dx. All right, and this is a problem for integration. We don't have a rule yet for this. So this is why we need the calculator. And a lot of these are this way because of the square root sign. Okay, so on the calculator, it comes out to be, there we go, integral 0 to 2 pi, square root 1 plus cosine x squared, 7.640. And if we go back real quick and look at the approximation we came up with, the Riemann sum with 12 subintervals was 7.633. So that's a pretty good approximation. Pretty good with only 12 subintervals. But the actual answer, the actual length of the curve is this number right here. Kind of neat, kind of neat, kind of neat. All right, let's tackle a couple by hand. So let's start with the linear function. We know the answer to this with geometry. We don't need calculus, but just go ahead and do it anyway. So the curve, or the line in this case, would look like this. And if we draw a triangle diagram, this is 4, this is 8. So the length here, using the Pythagorean theorem, is going to be the square root of 64 plus 16. Is that right? 64 plus 16, so the square root of 80. Or 4 square roots of 5. Should be our answer when we're done here. Okay? But let's go ahead and set it up. So we'll need the derivative of f, which is 2. And the length is the integral from 0 to 4 of the square root of 1 plus the derivative, which is 2, it's always 2, squared. That gives us 1 plus 4 on the inside of the square root, that's the square root of 5, and the square root of 5's antiderivative will be x square root of 5 from 0 to 4. Okay, voila, we've got 4 square roots of 5, which is what we expect from geometry. Okay, so it appears to work here. Now, the next one, or the problem we're going to have you do for your entrance ticket, is not a linear function, but go ahead and give it a try. 8.1, number 7. Try to apply the formula to that specific curve and that specific interval. Pause the video and then come on back for another example. Okay, so this one is probably going to be similar to the one you just did. But let's just go ahead and take a look at it. We've given an interval, we have a function. We need the function's derivative to calculate its length, which, by the way, if you think about what that means, as a side note, your function will need to be differentiable on the interval in order to calculate its length. Otherwise, this formula won't work. We'll have to maybe solve for x and integrate with respect to y, or otherwise it can't be done. Okay, so what's the derivative here? 3 halves times 2/3 will cancel, so we'll have x minus 1 to the half. And therefore, our length formula will be the integral from 1 to 4 of the square root of 1 plus this thing squared, which is just x minus 1, which is great. We're very grateful for that. And that's why a lot of these don't come out so nice, right? Because we got the square root. In this case, this square root got canceled by the squared in the formula. And what do we have now? We have just a very nice square root of x, or x to the 1/2, to do for an integration. Not bad. Our antiderivative will be 2/3 x to the 3/2. And we'll evaluate that from two nice numbers, 1 and 4. Oops, the 1 should be down there and the 4 should be up here, right? Okay, so we're going to have 2/3 4 to the 3/2 minus 2/3 times 1. And let's see here, 4 to the 3/2 is 2 cubed, it's 8, so 16/3 minus 2/3, so 14/3 is our length. Okay, very neat. And for your last entrance ticket problem, you can try same section, number 9. The algebra is going to start to get a little bit messy, as you'll see in class. So have that ready to go. Be excited. And please email me 2 questions you have on this lesson, and we'll see you in class. Bye-bye.